previous sessions, we've looked at how we can use integration to find the area under a function. What we're going to do in this session is actually take it into 3 dimensions and look at how we can actually generate an expression to find the volume using integration. So let's start off by imagining we've got a function that looks like this. And we have got 2 values, so we can call them a and b. And what we've looked at so far is how we could use integration to find the area between those 2 points. If I took this curve and revolved it around the x-axis, hopefully you can see that that would actually generate a 3-dimensional shape. And if I was to take a slice through this at any point, the cross-sectional area would be that of a circle. So wherever I cut it here, you can see that the cross-sectional area would be that of a circle. We can use that principle then to generalize or an equation. If we have a look at, this is just a simple case of the line y equals x between 0 and 5. So if this is our function here and we were to rotate this around about the x-axis, just think to yourself what kind of shape that would generate. Well, hopefully you can see that that would generate a cone, and that would have a volume which can be calculated geometrically using the formula for the volume of a cone, 1/3 pi r squared h, with the height of 5, and the radius here is also 5. So we could use that to generate the volume for that cone to give us 125 pi over 3 cubic units. But we want to generalize this using integration. So let's have a look at how we can start doing that. So let's go back to our initial function here. So we've got some function that looks like this. This is our solid. We can see revolving the function around the x-axis generates that. Each of these slices, if we were to work out the volume, would give us a cylinder. And as we've seen before, we want to improve the accuracy of the volume by increasing the number of cylinders in this instance. So we're going to increase it towards infinity, and at that point, that will give us the most accurate value for the volume. If we take a point here, so this is a point on the function here, xy. If we wanted to find the volume at this particular point, or one of these cross sections, so the volume of this particular cylinder here. So the width, we said we wanted an infinite number of cylinders here, so this distance, delta x, is going to be getting infinitesimally small. The volume is going to be calculated by finding the area. So the area of the circle is just going to be pi r squared. Now r, in this instance, the radius is going to be the y value. So the area of that circle is going to be pi y squared. And if we are trying to find the volume of the cylinder, we need to multiply by the depth, which is going to be delta x, which is going to be added onto the formula there. As the number of these cylinders increases to an infinite number, and the distance, delta x, or the depth of the cylinder becomes infinitesimally small, we're going to have the situation where this becomes the integral. So as the limit, as the thickness or the depth of the cylinder becomes tends towards 0, then we can find this by integrating between the 2 values for the function pi y squared with respect to x. And that is the general formula that we are going to be working with today. So more formally then, if we are trying to find the volume, if we have a function y equals fx which is continuous between a and b, and the region bounded by y equals fx, and the x-axis between a and b is rotated about 360 degrees about the x-axis, then the volume of the solid formed is given using this formula. So we've seen this version here. The definite integral between a and b of pi times y squared with respect to x. You can also see it in this format, which is just, more formally we're saying y equals f of x, so this is just f of x all squared, and that is obviously going to give us the same thing. So let's have a look at an example. Find the volume of the solid formed when the function y equals 1 over x is rotated about the x-axis between x equals 1 and x equals 4. This is what we're going to end up with. So here we need to find the definite integral between our two boundaries, 4 and 1, of y squared multiplied by pi. So here fx is 1 over x, so it's going to be pi times 1 over x all squared. That is the same as, we can take out pi as a constant, so pi times the definite integral between 4 and 1 of 1 over x squared. That is the same as using rational exponents, x to the negative 2, so we can therefore multiply pi by x to the minus 1 over negative 1 between 4 and 1, which is going to be pi times, this is going to simplify to negative 1 over x between 4 and 1. If you substitute in for 4 and 1, you will end up with the volume of pi times 3/4, which is going to give you 3/4 cubic units. Here are a few questions for you to have a go at, and then we'll come back and look at them together. So this first question, we've got y equals x squared, just using the formula between finding the volume between 3 and 1, we're going to find the definite integral of pi y squared. Y squared in this instance is x squared, so it's going to be the definite integral between 3 and 1 of pi times x squared itself squared, which is going to give you x to the power 4. And again, just using the definite integral, we can substitute in, and that's going to give us a solution of 242 pi over 5 cubic units. Second one, y equals e to the x. So here we're going to integrate between 2 and 0 for pi y squared. Y squared is e to the x, so that's going to be e to the x squared, which is going to give us e to the 2x. So integrating here, this is going to give us, again we've taken out pi as a constant, e to the 2x over 2 between 2 and 0. We can substitute in for x, and we'll end up with pi over 2 e to the 4 minus 1 cubic units. Y equals 4 minus x squared. If we rotate that around the x-axis, this is what we would end up with. So here's our function. Integrating between 2 and 0 for pi times y squared. Substitute in for y, which is 4 minus x squared, all squared, and we've taken out pi as a constant. Just a case of expanding all that, and then we can integrate and substitute in for our values of x, and we end up with 256 pi over 15 cubic units. Final question then was this one. We're going to substitute in for y, our function, which is the square root of 2x over x squared plus 1, and that's going to be all squared. Consequently, that's going to be 2x over x squared plus 1. We want to find the integral between 1 and 0. This we can recognize using the substitution rule is just going to be ln x squared plus 1. So we then need to substitute in for the values, and that's just going to give us pi times ln 2 minus ln 1. Right, let's have a look at a calculator question now. So, use a definite integral to find the volume of the solid formed when the region bounded by fx equals root 9 minus x squared and the x-axis is rotated 360 degrees about the x-axis. Verify your answer using a geometric formula. So we've got something that looks a bit like this, a semicircle. I'm going to rotate it around the x-axis. So we can use our formula. We're going to integrate, this is pi y squared, so y here is root 9 minus x squared. So when we square that, we will end up with, this will disappear, and we'll end up with pi times 9 minus x squared. If we substitute in fact we can put the whole thing in our calculator, we'll end up with an answer of 113. If you think about it using geometry, if you rotate this 360 degrees, you're going to end up with a sphere. You can use the general formula for the volume of a sphere using 4/3 pi r cubed, which is therefore going to give us 113 as well, so we can verify that. Use a definite integral to find the volume of the solid formed when the region under the curve y equals x squared between x equals 0 and x equals 2 is rotated about the x-axis. So again, here is our function. We know the general formula is going to be our function squared times pi, and integrate that between a and b with respect to x. So here, if we've got a function which is x squared and we square that, we're going to integrate between 0 and 2 pi times x to the 4. That's taking out pi as a constant, and then we can substitute in for the two boundaries, x equals 2 and x equals 0, and that ends up with an answer of 32 pi by 5.